You take a second derivative matrix, D2, and what it thinks of is this is the x and the y coordinates, as it were. So it says, don't do anything to y, take two derivatives in, sorry, don't do anything to x, take two derivatives in y, plus take two derivatives in x, nothing in y. Yeah? Length D2 is I have to make this I to be the same size as this. Length, yeah, size and length. But size gives you two numbers. It says, gives you two numbers, right? Length gives you one number, 20. Size gives you 20, 20. I want one number out of here to get this to be a 20.
So cron, I'm sorry, so this, that's really a command?
Cron? Yeah. Dude, I know.
Okay, so
do you guys all want to have beer over this later? Totally do that. It'd be awesome. No? Okay, because I'm up for it. No, okay.
it does what now?
So what cron does is basically, so remember how we played this whole game in class? If we have the lights on, it'd be great. Real quick. Remember the game we played in class? Hey, restack the matrix. Remember this? We took this matrix and said, oh, yeah, but we need to make it a vector. And then we got to figure out how everybody connects to each other. Cron does that. It's not like it's a, this is not magic. I made you do it in class, and we made it do it for B and C, but it works the same every single time, this connection of how it all connects. And so you just say, cron does that for you. It's a reordering, and it just says, okay, you're going to do that? Fine. By the way, you want it 2D, 3D, 4D, 5D, whatever you want to do. I'll set it up for you. I know how you reorder things. I know what you're trying to do with this. I know what you're trying to do this is take this matrix, multiply by one vector, and get out two derivatives in x and two derivatives in y, where I know you reshaped it. So that's what cron does. Okay? So, for instance, if you wanted to do reproduce the matrix A we did in class, okay, you remember the matrix A, which was two derivatives in x and two derivatives in y. All you'd have to do is take the 1D two derivative matrix, which is super easy to construct. Negative 2's in the diagonals, 1's on the off diagonal, 1, 1 on the corner. And all you got to do is say cron IA plus cron AI, done. There's no diagonals, 9 diagonals to put in to make sure they get shifted. It's all done for you. All done for you. So easy. Okay, but it's D, what? Then it's, I'm not actually sure. I haven't,
you got to use an I in there, or?
Yes.
Okay.
If you really want it, yeah. You can't do, so remember, so, okay, sorry. So remember, this is dy squared plus dx squared. When you're mixing them together, you're making uxx, uyy. That's different,
Okay.
right? So that's...
If you want uxy, you would do cron dd.
Yeah, so if you want u of x, y, yeah, you do cron d, comma d. Yeah. Okay, that's the hardest part of the code right there. Because the rest of it is going to just be using OD45. Okay? All right, so things we need to do. First, we're going to have to still work with the reshape of u into n squared by 1 points. So we're ready for our initial condition. That's little u. I got my derivative matrix, and now I can go solve stuff. So I want to solve this equation, so I say, okay, I need some t-span. Let's put some t-span in here from 0 steps of 0.2 to 4. I'm just making some stuff up. And I'm going to pull out some t. I'm going to pull out my solution. Let's call it u sol, OD45. And I'm going to throw in some right-hand side. This is the heat equation, right-hand side, in 2D, using Cheb. Okay, that's a long name. I usually don't like long names, but fine. I throw in my t-span. I throw in my initial condition. I'm not going to do anything with tolerances. What else do I need in there? Well, I need my Laplacian. Let's throw in there. That's kind of it. Here? What? Yes. Okay. That's it. That's what you're going to do. You got everything there, everything you want. You throw in your initial condition, which is a big vector. That L is going to take two derivatives in x and y. Your right-hand side is going to look trivial. We'll do it in a minute. And let's go here and just say, okay, I got that. What am I going to pull out? What comes out of this is u sol, which are these big, long rows. Remember, it's the data, 2D data, stacked at time 0, next time 0.2, 0.4, 0.6. So what you got to do is you got to plot that stuff, right? All right, so let's do the peak color on that. So what we're going to do is for j equals 1 to length t. And what we're going to do for each row, we're going to say, okay, let's pull out usol. Let's go pull out the jth row. And when we get it, we're going to reshape it back to what it's supposed to look like, n by n. And let's call that u plot. And then what we're going to do is going to do a p color on it. P color x, y, u plot. There we go. That's it. We might want to use some shading and terp on that. We also might want to maybe make that 30 instead of 20. Make it a little bit finer resolution. That's it. That's your old code. Okay? So let's go build that right-hand side function. File. File. New. Function. We want to build right-hand side. And what do we call it? Heat. Right-hand side, 2D, Cheb. See, this is why you don't make like long names. That's stupid. What was I thinking? So you bring in your initial condition, right? Or you bring in your time, and then you have your initial condition, u, and then you have stuff, and then you have L. And your right-hand side for that function, done. Sweet. That's it. Right? It's a heat equation. That's all you got to do. That's your whole right-hand side. Everybody agree with that, mostly? Yeah.
Wouldn't it be n plus 1? Instead of, like, if you go back to your...
Could be.
Instead of 10.
Oh, actually, sorry. In fact, let's do the following. So actually, you cut it up into 20 intervals, 21 points. Sorry, my bad, my bad. So you know what you could do here? There's a couple options for you when we're working with this. If you look at this thing here, you're putting an n. This is coming out to be 21 points, right? And so one way to easily do this is you can send in.
Why wouldn't you want to use all 21 points?
You can. But here, notice I'm doing everything reshaped. And I can either put n plus 1 squared here, or if I want to keep it as n, which is a little cleaner, I can just say n minus 1, which comes back with n. Same thing. Yeah. Everybody get that? I have, I'm working with as if n is down here. I have n points and I'm doing stuff with, but it's actually supposed to be n plus 1. So two ways to fix it. Either you make everything n plus 1 down here, or I make one little change there at n minus 1. And since I am lazy, and I'm having too much fun pre-funking, I'm just going to do n minus 1 so we keep the party going. Okay? So now we have 29 intervals, 30 total points. Okay? So, everybody good with this right-hand side here, by the way? Jeez. This thing tried to hop off again. All right. File, save as. Save. So there's my right-hand side. And that's all I need to do. By the way, your homework, you're going to add stuff. Right? You got a bunch of stuff there. Yeah, like u cubed, u squared v, v squared u, v cubed stuff. It's the only thing you're going to do different. And maybe you have a v field too, so you're going to just stack all this stuff together. But really, fundamentally, this is, once you have this, you're good to go. Okay, so now let's try to run it. Not that. Here it goes. And go. It takes a while, actually, provided it's actually running. Hey, look at that. It actually seems to be working on the very first try. Last time was a little bit of a cheat, right? I mean, just because we had that period in the wrong spot, that was so minor. Okay, uh-oh. What's it not liking? Oh! Snap. All right, fine. Wondering if, let's just check it out. Okay, there's my D matrix. Let's try to go this a little bit shorter here. And also, let's run it for a little shorter time. Let's see if I'm having some problems there with this thing. Because I have a picture of it there. Because we haven't talked about boundaries yet, by the way. Boundaries are very important to talk about. Ooh, look at that. Stuff's going on. Shorten the time span, yeah. So last thing, boundary conditions. And this is going to be important for us. In your homework, I say apply no flux boundary conditions. Notice that this D has no boundary conditions associated with it, and that's actually why this thing is blown up. You have this thing, and it doesn't know what to do with the boundaries, and then it affects the whole computational structure. So you impose boundary conditions directly on that matrix D or D2.
Yeah, I'm sorry. The boundary condition was you this Gaussian, right? That was your boundary condition.
No, this is just initial condition.
Oh, initial condition.
Yeah. The boundaries all get enforced from the derivative matrix, right? Because that's the one thing that's actually acting on the system and enforcing a boundary, right? So right now I'm not enforcing anything. So I'm going to enforce some boundary conditions. And the ones I'm going to enforce, which are relevant to you, are to make the first and last row of D2, and we'll talk about this more in the future lecture that was the past, is the following. First row, everything, is equal to zeros. So it's a okay. Actually, I think I just say zeros. It's a 1 by n. Sorry. Okay, there we go. And then the last row is also zeros. Okay.
So I'm sorry. What is this doing now? So originally, I mean, when you first ran.
So now I'm going to
initial
impose.
condition,
Yeah.
and it did its thing, and that's a legitimate solution.
I didn't have any boundary conditions. The boundary conditions of this I'm going to impose right now are at the edges, and that's at, and then, sorry. So out at the edge, I want, so actually, generically, here's what I want. At the edges, no flux boundaries. The derivative is 0 at the edge.
So the result you got before you imposed a boundary condition was a legitimate result, just without that condition, or it was just not a legitimate.
There was no imposition of any boundaries at all.
Okay.
So that's a problem, actually. If you don't impose boundaries, it's doing something with its boundaries that probably is not good.
That nice little picture with the colored corners was
No,
meaningless.
meaningless, yeah. But now, hopefully, we have added meaning. Yeah.
Did you say 0, or does that not matter since it's just
It's a little more complicated than that, as I will show in the future lecture. Okay, there it is. All right, so let's watch it again. For let's do the following here. I'm gonna watch this again. So now we can run it out a little longer. Let's go it out to like time 10 and start every 0.5. So we can just run this a little bit longer, and then we'll watch the movie. Okay? I know, exciting times. And by the way, we're going to watch it a little different. We're going to do Surf L, a lit surface with shading and terp. You'll like this. Still running here. Okay. Hold on. No, it's coming. Don't, just wait for it here. It's almost there. Come on. It's only going 10. It's not that hard. Come on. You could do it. You could do it. Heat equations are notoriously, they go slow. by the way. So this is when you, if you look at your homework, I have you do a very small n value. The other thing too, okay, in fairness, okay, let me do the following. Just real quick, we'll watch this movie again right there. Oh, come on. No, come, no. Okay. Did we go too fast? I know. Someone's at the door. Listen, tell you what. You can do this. One last comment to make. Here's something that's important to keep in mind. That L matrix, it's huge. Well, it's not that big. I cut it up into 30 points, right? So how big is 30 squared? Not that big. 900 by 900. Here's the difference. It's full. You never want to work with a full matrix. Ever in your life if you don't have to. It's full. This is why it goes slow.